Today we're looking at our last method used for factoring. And to do that, what we're going to see today, we've figured out methods to factor out something out of all terms. We've learned methods to factor polynomials with 4 terms and 3 terms. And today is going to be 2 terms. So that's all we have in this polynomial that we're supposed to factor is 2 terms. The deal is we must be able to square root both of the terms, and there must be a minus sign between the 2 terms. If you're wondering what the A and C come from, it would be if our polynomial looks like this. We likely won't see a x term. We could, but we likely won't. As we think about square rooting values, it's helpful to have these numbers in blue somewhere on the assignment or the notes, wherever we're going to be doing this. So anytime I realize that we're using difference of squares, I just write these down real quick. It's 1 squared, 2 squared is 4, 3 squared is 9, 4 squared is 16, so on and so forth. The more you know these numbers, the better. And then maybe even having that list above it. Do you know that the square root of 64 is 8? That would be helpful because 8 squared is 64. Now the square root of 64 is also negative 8 because negative 8 times negative 8 is 64. But we're going to keep things positive today. To figure out if we can factor something that looks like this, we're going to divide any GCF out we can first. And our goal as we're creating GCFs or factoring out GCFs is to make sure that we have some perfect squares. Both values, the A and the C, are square rootable. We'll square root both terms, and then whatever our answers are to the first term, I'm going to call that the square root of A. That's going to go right here. And right here. Yep, the same value in 2 different spots. And the square root of the second term is going to go right here. The same value in 2 different spots. However, notice that one of these second square rooted values will be added and one will be subtracted. That's how, when we square, we get a negative C. Positive times a negative is a negative. So let's give this a shot. There, in example 1, there's no GCF, but 9 and 16 are perfect squares, and it's not just the 9 that we're going to square root. The square root of 9 is 3. The square root of m squared is n. And then, if you think about that, isn't 3m times 3m 9m squared? Not only do the numbers have to match up to produce that perfect square, but the variables have to work out too. So 3m is going to be what goes at the start of each of my binomial factors. The square root of, so it's a binomial, there's a subtraction sign there, and I'm figuring out that I can square root both terms. That minus sign is critical. So the square root of 16 is 4. So I'll go plus 4 and minus 4. Boom. If you were to FOIL this back together, you'd get 9m squared minus 16. What about the middle terms, that bx as we called it? You would get a 12m, and you would get a negative 12m. What happens to those? Adios. They make 0 when they combine. B to the 4th. What's the square root of b to the 4th? That's going to be b to the 2nd. Notice, folks, I'm thinking I can proceed with this. I have 2 terms. They're being subtracted, and I believe I can square root both of them. B to the 4th is definitely, square rooted is definitely b to the 2nd. Because b to the 2 times b to the 2 is b to the 4. We add our exponents as we multiply the same bases. Square root of 16 is 4. So plus 4 minus 4. If you want to be a rebel and throw the minus sign in first and the plus sign in second, that's 100% okay. Hey, this next one, we've got two terms. They're being subtracted, and I think I can square root each one of them. Square root of x squared is x. Square root of y squared is y. So we'll go x minus y times x plus y. Look at that, I made that rebel move where I switched the plus and the minus sign. It doesn't matter, still is right. Hey, 49 and 25, here in example 4, two terms being subtracted. They're both perfect squares, however, square rooting u to the third is not going to work out very well. So I'm going to pull out a GCF here. That was the first thing they recommended if things aren't going smoothly. So I'm going to try that. So then when I pull out a u, which is the lowest degree I see here, I get 49 u squared minus 25. The deal is, if you have a variable and you're trying to square root it, the exponent has to be even. That way you can divide it by 2 or split it evenly. Kind of like how I split the b to the 4 up evenly into b2 and b2. Make sure we bring our GCF down. So we have 7u plus 5, 7u minus 5. 7u times 7u is 49u squared. Two more. Here we have even exponents, but notice that the bases are the same. So while 144 and 9 are exciting because I know they're perfect squares, let's factor out a GCF. Let's pull x squared out with our smallest degree that both terms have that base. So we're left with 144 x squared minus 9. You know what's interesting is I think 144 goes into, or 3 goes into 144. Let's play with that in a second. I think you get 48. But that wouldn't be good because you can't square root it, so we better keep things that way. So the square root of 144 is 12x. The square root of 9 is 3. But then we do it again with the minus sign. Boom. Last example. Seeing two terms, they're being subtracted. That's cool. Can I square root both of the terms? This x squared, I know I can square root into x. But 75 is not a perfect square, nor is 27. So what's a factor I can take out of both of these that make them become perfect squares? This 75 is kind of a tip-off. It ends in a 5. Are there any of our perfect squares that end in 5? 25. So if I divide that by 3, I think I'll get 25. We'll see what happens with the other number. So I get 25x squared minus 9. Hey, that 9's a perfect square too. That's fun. Bring down your GCF. So the square root of 25 is 5. Square root of x squared is x. Plus 3, because that's the square root of 9. And then do it again with the minus sign. There we go.